Hello everyone out there, wherever you are, whoever you are. This is almost human contact, isn't it? This is as good as it gets these days. So I'm delighted to be here today. My name's Martin Woolley, as there on the screen. Hopefully you can see that. And I work for an organisation called the Bluetooth Special Interest Group. Now, I can usually rely on people having heard of Bluetooth, but people are not necessarily aware of who the Bluetooth Special Interest Group, or the SIG, as we call ourselves, are. So think of us as the organisation behind Bluetooth, but we're not a manufacturer. We don't make Bluetooth components. We don't make software stacks or electronics components or stuff like that. There's no warehouse with all the Bluetooth in it behind our office. We're actually a standards organisation. So the primary outputs from the work that we do with other organisations all around the world, other manufacturers, is a large collection of engineering specifications that define how Bluetooth works and how it must be used in different types of products. So the purpose, of course, of doing this, of having a standards organisation kind of governing the specification of Bluetooth and its evolution, is so that every manufacturer using Bluetooth in its products does so in the same way, and products from different manufacturers become interoperable. So that's really who we are and what we're about. We're all about interoperability. Got 35 or so thousand companies who are members and contribute perhaps in various ways. So very much an engineering-led organisation. Now, I do speak at a good few technical conferences each year, and I tend to come along with, a topic to talk about, like most sensible people do. But today I thought I'd talk about a collection of topics rather than just one. And the reason for the topics I've chosen is they afford us the opportunity to kind of look underneath the hood a little bit, learn more about how Bluetooth works and what it's kind of good at and how that is achieved. And hopefully you can use that knowledge to achieve better results in applications and products and so on. That's the theory anyway. So I'm going to start off with some real basics. I'm not going to dwell on the basic stuff, but I just want to make sure everyone has at least the foundational knowledge to make sense of some of the more advanced things that I cover later on. So let's make a start. So the first thing to know is that there are in fact two quite distinct Bluetooth communications technologies. They're both branded the same, so you won't necessarily know this by looking at the box of a product that you've bought. But the first one's called Bluetooth BR-EDR. That's its technical name. That's basic rate. Enhanced data rate. That's actually the original Bluetooth. It's over 20 years old now. You can think of it really as being a cable replacement technology. So products that used to be connected by a cable, like a mouse or an audio headset, the cable got thrown away, and instead there was a direct wireless communication afforded by Bluetooth BR-EDR. And it's old, but it's still very popular. It's the go-to wireless technology for audio products, including the headset I'm wearing right now, for example. But newer and in many ways much better is Bluetooth Low Energy. So Bluetooth Low Energy is very power efficient, so much less drain on batteries, for example, and it's very common to find devices that will run off tiny coin-sized batteries for many years, or that use energy harvesting techniques to generate the power they need to operate and communicate. But that's not the only thing that's good about it. It's much more versatile as well. So you can form those point-to-point connections between two devices, just as you can with the old Bluetooth. But it's also able to broadcast, which means that one device can communicate in a connectionless way with an infinite, absolutely unlimited number of other devices, provided they're in range. So that's really powerful. If you've heard of Bluetooth beacons use this broadcast capability. It's also possible, though, using a technology called Bluetooth mesh networking, which is based upon Bluetooth Low Energy, to create mesh networks of quite large numbers of smart devices. And I'm going to talk a little bit about mesh later on in this talk. In fact, just to give you a sneak preview, I'm going to talk about reliability in communication. I'm going to talk about range, and I am going to talk about a certain aspect of mesh networking with a very short primer for people who for whom it's a new subject. and a little look into the future as well as to the sorts of things that are coming for Bluetooth. So 2 types. I'm talking about Bluetooth Low Energy today. Some basics to know about Bluetooth Low Energy from a developer's point of view, though, is that devices can behave in different ways depending on the role that they assume, and this is controlled by their firmware. Now, some devices will do something called advertising. This is broadcasting data about themselves, perhaps a name, perhaps some hints about their capabilities and therefore what type of device that they are. And they do this so that they can be discovered by other devices like the smartphone in my illustration here, which will be scanning. Scanning means listening for these broadcasts. And in a typical application like this, the smartphone application doing the scanning is receiving packets broadcast by devices around it. It will filter out those that seem to be from irrelevant devices, present the user with a list of those devices in the environment that seem to be of the right type, and the user will then pick one, and the smartphone application will connect to it. And you'll see there that that peripheral is no longer advertising. And I kind of just gave the game away there because there's some technical terminology here. Part of the Bluetooth stack is called the generic access profile, or GAP. It's where these roles and behaviors are defined, and GAP peripherals are the types of device that advertise and can be connected to, and GAP central is the name of the device role, which can scan to discover devices and then initiate a connection to them. So sneaking out here is also already the concept of connectionless versus connection-oriented communication, the 2 broad ways in which Bluetooth can be used. Now, once you've connected to a device, you move into a different area of the stack called GAT, which is the generic attribute profile. And devices, those peripheral devices, once discovered and connected to, they contain a table of data items called the attribute table. There are different types of attributes, and they form a kind of hierarchical structure. So at the top of that hierarchy, we have things called services, and services are really a grouping mechanism that provide context for the things that they contain. Services provide things called characteristics. That's really a fancy name for a data item. Characteristics have a specific type identified by a UUID. They have a value. They have some properties which indicate what you can do with them. You know, can you read the value, write to it? Can you have value streamed from the remote device to your device? That's something called notifications. And they have permissions, which are to do with security. Services always have characteristics inside them. Characteristics can have 0 or more descriptors attached to them. So that's the 3rd level in the hierarchy here. And a descriptor is something which either provides metadata, some more information about the associated characteristic, or in some cases, configuration flags that let us do things like switch on or off certain behaviors. So one of the operations, the things I can do with a characteristic is if it supports it, I can say, hey, please tell me whenever your value changes, or tell me your value every second or something like that. That's called notifications, and it's via a descriptor that we can switch on or off that stream of values from a particular characteristic. So that's that hierarchy, the attribute table. And the class names at the bottom there come from Android, just as an example of the kinds of classes you're likely to see in various platforms. This will always be available, the names will vary. So on screen, what I have now is one example of what the Bluetooth Low Energy stack can look like. It's actually modular, so what parts of the stack a device have will vary, and some of the parts are optional. Excuse me. The major blocks there are the 2 main parts of the stack. So at the bottom, the grey block is called the controller, and that's where all the low-level stuff takes place. It sits right on top of the radio transmitter receiver, which is hardware part of the device. The blue block at the top is called the host. So we split the layers of the stack across the host and the controller. They are connected via one of several potential sort of physical transports like USB or UART. But there's a logical interface which is comprised of commands that are sent by the host to the controller and events that go from the controller up to the host. So that's how they talk. Whatever the physical underlying transport is that connects these two components, which, by the way, may be from different manufacturers, we have a consistent logical interface that allows them to communicate. Most devices have a stack that looks something like this. There are some exceptions I'll show you later on. So with those basics under your hood, I'm going to talk about reliability now, because largely I chose this because I wrote a paper on the subject last year, kind of understanding reliability in Bluetooth communication. I think was the title. It's on our website, should you find you're interested. It's actually a very big topic, and Bluetooth has all manner of things kind of built into it to make communication as reliable as possible. Some highlights here because I'm short of time, of course, but let's make a start. Here's the problem. So a stack is multi-layered, of course, but right at the bottom of the stack, we have the physical layer where the physical medium that we're using to encode and convey information sits. And with Bluetooth, as with many wireless communications technologies, the physical medium we use is radio, which is a form of electromagnetic radiation. Sounds like we're going to have a physics class here now, but don't worry, we're not. But that's what we're using way down at the bottom of the stack. But radio itself has all sorts of challenges and problems. It's not an inherently reliable medium for using in this way at all. So it's like building on shifting sands, to use the old adage. Happily though, if you build the right things on top of your radio physical communication layer, if you do the right things in your protocol design, then very highly reliable communication can be accomplished, even though the underlying basis, the foundational stuff, is itself extremely problematic and there are all sorts of challenges. And Bluetooth definitely exemplifies this in a number of ways. So let's explore that now. Here's one of the key challenges. I'll run you through a few of the problems that have to be solved first of all. So when a device transmits a packet, it does so within a radio channel. And a radio channel is defined by an upper and lower frequency. So there's a kind of range of frequencies. And if you're transmitting somewhere in between that upper and lower limit, then you're using that channel. Now, if another device transmits on the same channel at the same time, or in a way which overlaps with another packet, we have what's called a collision. And those two transmissions will corrupt each other. So obviously, if you think about it, the longer it takes to transmit a packet, and the more often devices are transmitting in a given environment, then the more likely it is that collisions will take place. There's a probability kind of aspect to this. So transmissions colliding with other transmissions using the same channel can be a big problem. If you're aware of how your Wi-Fi works at home, of course, the concept of channels applies there. You will have picked a channel on your router or accepted the default, and all will be well, of course, unless your next door neighbor is using the same channel, in which case you may find you have some reliability or throughput problems. And it's because of exactly this problem. It's common to all radio communications technologies. Two other problems, coexistence. Now, Bluetooth operates in what's called the ISM band, that's industrial, scientific, and medical. That's the name we give to the 2.4 gigahertz band. And of course, Wi-Fi can use that. DECT phones can use it. Zigbee can use it, if you've heard of Zigbee. So it's quite a crowded part of the radio spectrum, and it's busy and popular because it's free. There are no enormous costs associated with using it, so it's very popular. Now, coexistence relates to the set of problems and challenges that are a consequence of sharing the same part of the radio spectrum across different technologies. Co-location, on the other hand, is all about an individual device that supports multiple technologies. So smartphones are a great example of this. You know, they support Wi-Fi and Bluetooth and LTE, which is the technical name for 4G. And different, having multiple radios in a single device can give rise to interference and other types of conflicts as well. So these are the kinds of problems you have to deal with in designing a protocol stack. So I'm going to talk now about how Bluetooth goes about achieving reliable communication despite these shockingly complex problems. So we'll start here. So down in the physical layer, The first thing we're concerned with is this. We're using radio, but how do we use radio to represent the digital constructs that we know and love called bits, which have a value of a 1 or a 0? Because radio is analog. Don't be fooled by terms like digital radio. It's analog, end of story. So a physical layer in any protocol stack that uses radio has to select something called a modulation scheme. This is a way of harnessing the fundamental properties of radio signals, of waves, to represent binary data. Now, you can use all sorts of properties of radio waves. You can use the frequency, you can use the amplitude, you can use radio phase. You can use these things in combination. It so happens that using amplitude produces systems that are much more vulnerable to interference in the environment than modulation schemes that use frequency. So the first thing to know about Bluetooth is that it uses a frequency-based modulation scheme. It's called GFSK. That stands for Gaussian Frequency Shift Keying. The frequency shift part works like this. So within a given channel, there's that upper and lower frequency limit that defines the channel. There's a central frequency. If I want to transmit a signal that represents a value of 1 in that channel, I take the central frequency and I shift it up by an amount called the frequency deviation and transmit a signal for a certain length of time. And that signal is called a symbol. It's an analog representation of the binary value 1, okay? If I want to represent a 0, I shift the signal down by the same frequency deviation. So by modulating the frequency, I represent my 1s and my 0s. There's a problem with doing only this though, because abrupt changes in frequency generate noise in the electronics. So the Gaussian part of Bluetooth's use of frequency shift keying involves a filter which smooths those frequency transitions, and that reduces noise and makes this a really solid underlying basis for everything that's built on top of it in the rest of the stack. So what are we actually transmitting? So all Bluetooth Low Energy packets have the same fundamental structure, regardless of what we're using it for. And some of the fields in what we call the air interface packet are there to help us achieve reliable communication. So the radio receiver receives a packet one symbol or bit at a time from the working from the left on my diagram, left to right. So the first field received is called the preamble. All this is an alternating pattern of 1s and 0s. And its purpose is to allow the receiver to figure out exactly what frequencies the transmitter is using for those 1s and those 0s so it can really lock into them. The second thing it does, it lets the receiver adjust its gain control, which is to do with amplification, to get the signal just right and the way we're locked into it, so it's just right for subsequent use. The next field is called the access address, and to understand its purpose, you need to understand this. At this stage of the story, the radio receiver is receiving everything. All radio signals that have a frequency that falls within the channel it's currently tuned into. So that includes Bluetooth packets that are destined for this device, we want those. Bluetooth packets which are destined for other devices, we don't want those. Packets relating to other wireless technologies, maybe Wi-Fi, and background noise at the very least. So the radio doesn't know anything at this stage about protocols. It just knows it's received a signal that's in a given frequency range. So the access address helps us separate the stuff we want from the stuff we don't want. And the way that works is that there's a special kind of magic number, it's a 32-bit value, defined in the core specification that is always used when we broadcast a packet which is available to any listening device. Okay, that's the nature of broadcasting. It's a one-to-many communication system. For connection-oriented communication, every connection has a unique access address. So, of course, our radio knows which access addresses it cares about. And using the access address, therefore, it can discard anything that's irrelevant to this device. Moving over to the other end of the packet layout here, we have the CRC. That's a cyclic redundancy check. You may already be familiar with this term. And this allows the receiver to detect cases where errors have been introduced, possibly due to something like collisions. So the transmitter, when it formulates a packet, the other fields get filled first. It then calculates the CRC value from the other bit values in the remainder of the packet, tacks it on the end, transmits the packet. The receiver does exactly the same thing. It receives the packet, it calculates its own CRC value from the bit values in the data it just received, and it then compares its calculated CRC with the received CRC. If they're the same, everything's good. There was no corruption. If they're different, something went wrong. There was probably a collision or something like this, and the packet will be discarded. The MIC is, strictly speaking, not to do with reliability, but I kind of included it anyway because I think it has relevance. So Bluetooth Low Energy packets can be encrypted. That's very common. So if your devices are paired, then communication will be encrypted between them. And all encrypted packets have this MIC, message integrity check field. Now, this is actually a security field, and it's more common to call fields of this type actually a message authentication code. That's the term used in security circles, but MAC means something else in the world of communication as well, media access control. So rather than confuse everyone, we call this an MIC, but it's a message authentication code. And its job is to let the stack detect when there has been some deliberate tampering with our encrypted packet, because you could change values maybe of a packet in flight, recalculate the CRC, so the CRC seems to work, but this is a cryptographic check that lets us check for tampering, okay? So packets can change accidentally because of the environment or deliberately because of malicious tampering, and the MIC protects us from that. Spread spectrum, right, this is probably the most important area of the topic of reliability in Bluetooth. I've already mentioned the 2.4 gigahertz band. So this is not a frequency that Bluetooth transmits on. It's a band. It's a big chunk of the radio spectrum. And Bluetooth divides it into 40 different channels, each of which is 2 megahertz wide. It then uses multiple channels in its transmission of packets between devices. So this is a very big differentiator between it and the way, say, Wi-Fi works. So Wi-Fi, you pick a channel, that's what your system, what your router uses, and all the devices that use your Wi-Fi network are going to use the same channel. Bluetooth doesn't work like that at all. It will spread packets from a device across different channels within the ISM spectrum in a variety of ways, depending on whether we're doing connectionless or connection-oriented communication. And by spreading packets across the spectrum like this, the probability of collisions is very substantially reduced, and it lets Bluetooth work really well in very, very hostile radio environments where there are very large numbers of devices. I'll tell you more about how that works in a moment. Excuse me. So in connection-oriented communication, so two devices have connected. 37 of the 40 available channels get used. I'll tell you what the other 3 are used for in a moment. What you're looking at on screen here is a histogram produced by a protocol analyzer that I use in my work, and it's showing the distribution of packets across channels during some testing I was doing between 2 connected devices. You can see some gaps. Those are the other 3 channels that are not used. Now, the way in which packets get distributed is through something called adaptive frequency hopping. So there's a channel selection algorithm, and at intervals, which can be as often as every 7.5 milliseconds, the channel changes and a number of packets get transmitted and received on that channel. That's frequency hopping. The adaptive part is really interesting though, because devices also monitor how well each channel is performing. If they're seeing a lot of errors on a particular channel, lots of CRC failures, for example, the channel will be marked as not to be used because it's not working properly, and the other device will be told, hey, this channel doesn't look like it's working too well, let's stop using it, okay? And so the system adapts to the environments that the devices are operating in. If it transpires that one end of the spectrum is saturated because of some other devices that are really hogging that set of channels, they don't get used anymore. So it's very, very efficient, very smart the way it adapts to the conditions that it finds itself in. That's adaptive frequency hopping. And that's a spread spectrum technique, and it's used in connection-oriented communication. When we're doing connectionless communication, so we're just broadcasting, this is where the other three channels get used. But they're used in a slightly different way. So the way advertising works, that's the term we use for broadcasting, is we send a copy of every packet on each of channels 37, 38, and 39, okay? So even if one part of the spectrum is saturated in some ways, lots of interference, a copy of that packet should get through on one of the other channels. So this is a simpler form of spread spectrum. And the other thing that we do as well, advertising takes place at specified intervals. However, rather than that locking that into a strict timeline, strict schedule, we introduce some jittering. We introduce random perturbation, I think is the technical term, reading my own slide there, so that the scheduling is slightly randomized by up to 10 milliseconds. And that prevents us experiencing persistent collisions with other devices that happen to be advertising on the same schedule in the same environment. So it's a simpler form of spread spectrum, but it's quite effective. And in fact, the last thing to know, and again, this is from my protocol analyzer, channels 37, 38, and 39, those are their channel index numbers. Physically, in terms of where they sit in the ISM spectrum, they're actually spread quite a long way apart. There's a distinction between channel number and channel index. So channel index is 37, 38, 39, and 39. Big gaps between them, and you can see them in use here on my screen. And again, the point here is that if one end of the spectrum, one part of the spectrum is saturated, is performing very badly, doesn't matter, because we've got other channels supporting connectionless communication that are a considerable distance from the area which is experiencing the interference. So spread spectrum in those two modes of communication, pretty important stuff. That's all I want to say on reliability. Again, I've got a whole paper on this subject if you're interested in knowing more. There's a lot more to it, actually. I'm going to switch topics now and talk instead about how we might maximize application data transfer rate. Now, this is a kind of special topic in the world of Bluetooth Low Energy because normally you're dealing with small amounts of data. Normally the use cases are to do with monitoring, control, automation, small amounts of data being transmitted between devices to send commands or to receive readings from sensors, this kind of thing. Those are the primary use cases. There are, however, occasions where you have a larger amount of data, and if only to give a better user experience, you want to transmit it as fast as you can. Good example would be a firmware update. You want to update your activity tracker on your wrist over a Bluetooth Low Energy connection from your smartphone. And there's a good old chunk of data that's got to be transferred across. How can you make it go as fast as possible? So there's more to this subject than meets the eye as well. At the very bottom of the stack, I've already explained some of how the physical layer works and how modulation schemes work and how we represent those ones and zeros. The raw material for the speed at which data can be transmitted is called a symbol rate, because don't forget the analog equivalent of a bit is called a symbol, okay? All Bluetooth Low Energy devices support a symbol rate of 1 million symbols or bits per second. One symbol is synonymous with 1 bit in the digital world. So 1 mega symbol per second, and it's called LE1M, that's capability of the physical layer. That's our raw material. So that sounds great. We can get 1 million bits per second, but not so fast, because unfortunately not all of that transmission rate is available to us for application data. The protocols themselves, of course, have data that they contribute to every packet. So here's an example that helps us understand what we really mean by application data rate. So on screen there, we have a packet that I've captured. Highlighted in yellow are 2 bytes. Those 2 bytes are my application data. That's it. The rest of it is protocol data. So I've got 168 bits in total. That's my packet length. Only 16 are application data. So if you do the maths with 1 million bits per second, I'm really only getting 95k bits per second when measured at the application layer over that 1 million bits per second underlying physical symbol rate. Now, the overhead of the protocol fields in the kind of header in the packet, if you like, is fairly constant. So one of the strategies for increasing application data throughput is to increase the proportion of application data in each packet. That's a key strategy. So how can we do that? Well, there's a concept of the MTU. This is a maximum transmission unit, and it says how big a PDU or protocol data unit can be. And every layer in the stack has its own MTU that governs how big the packets are that it can handle. Excuse me. Now, when 2 devices are communicating over a connection, most of the time, most typically, they're using something called the attribute protocol, because that's how we work with that attribute table that I described in the basics slides at the beginning here. And the attribute protocol has its own MTU, which by default is only 23 bytes. It's very, packets are small. Fortunately, the attribute protocol includes a PDU called exchange MTU. And if one device sends it over the connection to the other device, it will come back with information about the largest MTU it can support, and they figure out what the largest MTU size is that they can both support and adopt that for the remainder of the session. So you can go as high as around 512 bytes for your attribute protocol packets, but what you actually get will be very device dependent. And this is available in all Bluetooth Low Energy devices. Looking a bit lower down the stack though, sitting underneath the attribute protocol, we have something called L2CAP. That's an abbreviation, in fact, for Logical Link Control and Adaptation Protocol. It's the lowest layer of the host part of our stack. And one of the things it has to do, bearing in mind that the controller is a separate component, perhaps from another manufacturer with capabilities of its own, capabilities and constraints, is the attribute protocol PDUs that are passed to the L2CAP layer will get chopped up into link layer packets that the controller on the other side can support. On the other side, I mean connected to or associated with this host. So there's some chopping up in our large attribute protocol packets, which we like very much because we can pack lots of application data into them. So the overhead of protocol data is reduced. We kind of lose that when we get here, potentially, because we end up with lots of link layer packets. So that's not great. We don't really want that if throughput is our goal. Fortunately, from version 4.2 of Bluetooth onwards, and we're at version 5.2 now, by the way, 4.2 is 6, maybe 7 years old, I think. There's something called LData packet length extensions. It's a feature which, if both devices support it, will automatically be used, and it ensures that larger link layer packets are used so we retain the benefits that we were looking for with our larger MTU size. So if you have any control over the devices used for your solution, and enterprise organizations often do because they issue devices to their staff, make sure you're choosing ones with a nice recent version of Bluetooth, because you'll get this benefit. Last thing, second to last thing, in fact, to know about before we talk about what can be achieved is the concept of a connection event. This is a really key concept in the world of Bluetooth. Radios in Bluetooth devices are what we call half duplex devices. They can transmit, they can receive, but they can't do both at the same time. And in a device like a smartphone, which can support multiple connections to multiple peripheral devices at the same time, that radio has to be shared somehow. So Bluetooth uses a time sharing strategy, if you like, and at agreed intervals, something called a connection event occurs. And at a connection event, which is associated with a particular connection, that's the time at which a given connection is allowed to use the radio to exchange some packets with the other device it's connected to. Now, Connection intervals can be anything from 7.5 milliseconds to 4 seconds. So very frequent access to the radio to very, very occasional. And obviously, if we want to go fast, we want to transmit data as fast as possible, we want our connection to have as frequent access to the radio as it can. So we want a short connection interval. Now, depending on the platform you're working with, you'll have more or less control over this. If you're an embedded software engineer, you'll probably have total control over what connection intervals are that you can accept or accommodate. If you're working on a smartphone platform, that's not going to be the case. Android in particular, which I know better than iOS, which is why I'm using it for examples, gives you a choice of 3, and they're not quantified. You can say, I want to go fast, so I want short connection intervals. I'm more concerned with battery life, so I want very long connection intervals, or I want something in between. And you can see those figurative constants there on the slide. So choosing the right or influencing the connection interval is a very important thing in achieving faster throughput. Last factor, I think it's the last one. I've mentioned LE1M, so this is the physical layer operating at 1 million symbols or bits per second. Newer devices also support something called LE2M, that's 2 million symbols or bits per second. Now, both devices have to support this version of the physical layer for this to be usable, but they can discover their respective capabilities. And once they've agreed they're going to use LE2M, things will go faster, but they won't go twice as fast. You might think that because the raw speed is twice as fast at the bottom of the stack, I'll experience double the speed at the application layer. But as I'm hoping you're appreciating now, there are lots of other factors, and that won't necessarily be anything like the case, but it should go faster. You'll certainly get what we call improved spectral efficiency, which means your packets are in the air for half the time because the symbol rate is faster. And that, of course, reduces the probability of collisions happening. So you get a throughput improvement and you get a definite reliability improvement as well. Oh, actually, there was one more. I keep saying the last factor. Here's another factor. This is the last one, I think. When you're transferring data, you're going to be using the attribute protocol via some APIs. And those characteristics in an attribute table in a remote device may support something called a write-up operation, of which there are 2 types. And this is what we'll use as the basis for sending data. We're going to write to the value of a remote characteristic. And the 2 forms are write requests, for which there is a corresponding response PDU, and write commands, which are kind of fire and forget. You're just writing it one direction. The big difference between the 2 from a throughput point of view is that with write requests, you have to wait for the response to that request before you can send the next request. So that's going to kind of proceed in lockstep, request, response, request, response. It's very reliable, but it's slow. Write commands, on the other hand, they're very, very fast, much, much faster than write requests and responses, but there is the chance of losing some packets because the other end of the connection, whilst there are acknowledgements happening at the link layer low down in the stack, so we do know if the device, say, has gone out of range. What we don't know is if we execute or send a write command packet, we don't hear, well, so we do get an acknowledgement from the link layer, so we know it made it there to the other device, but does it make it all the way up the stack to the application layer? That we don't know. What if there's buffer overflow? We could overwhelm the remote device and lose some packets here. So there's a trade-off here between reliability and throughput rates. So you need to be careful with your choice. I did some benchmarking on Android, wrote a simple application. Very quickly going to show you what that looked like now. Did have my phone on so I could keep an eye on the time. Okay, you were good. What I did was I wrote an app to transfer 100K, first using write commands, the fast version, then using write requests. And in each case, I first of all ran my test with defaults, and then I took control via the APIs and increased the MTU, chose the LE2M faster 5 physical layer, and asked for the fastest connection interval I could get. And 100K using write commands took nearly 8 seconds. But then when I tweaked my application to optimize My use of Bluetooth, I got that down to just over half a second. It's a massive difference. And if you think about that in terms of user experience, that is a tremendous improvement. Requests and responses, on the other hand, were shockingly slow. As you can see, 500 seconds. But with some tweaking, I got that down to 10 seconds as well. So understand the underlying basis, look for APIs that let you tweak these variables, and you can achieve great things. Let's talk about range next. Lots of people think the range of Bluetooth is 10 meters. Some think, oh, it must be 20 meters now. This is myth and legend from 20 years ago. It's hundreds of meters now, and in fact, considerably more. Let me explain the basis of range constraints and then what the state of the art is today. So, going out of range doesn't mean that the signal from the remote transmitting device is no longer detectable. It doesn't mean that at all. What happens is, as we get further away from a transmitting device whose signal is emanating outwards in a kind of sphere, actually, with an ever-expanding surface area, is the energy of that transmission is spread across a larger and larger surface area as we get further away, and thus at any point on that wavefront, the energy is going to be much lower because it's shared across a much larger surface area. So signal strength drops off very quickly, actually follows an inverse square law. Meanwhile, in the background, there is always background electromagnetic radiation caused by other machines and natural sources. As our transmitted signals level gets closer to the background noise, what we call the signal to noise ratio is changing. And when the signal to noise ratio gets lower, we get closer to the level of background noise, it becomes difficult to properly decode the information in our signal, and we start to make mistakes. So bits that were encoded by the transmitter to represent a 1 get translated to be a 0 by the receiving device. And of course, we detect this with the cyclic redundancy check. The Bluetooth spec says we can tolerate a bit error rate of no more than 0.1%. Any more than that, and it's not working. And it's there that we've hit our range limit. Fortunately, there's a technique called forward error correction that helps us with this. Now, I've already told you this at the physical layer. We can use LE1M and have 1,000 megasymbols per second, LE2M to go twice as fast. There's a third variant called LE coded, and this uses this forward error correction technique, which is a mathematical technique which takes additional data that's been added to packets that were transmitted and can use it not just to detect errors, excuse me, but to correct them as well. And this makes devices much better able to work properly, even when the signal to noise ratio is very low, which it will be when we're at a much greater range from the transmitter. And this improves, we call this the receiver sensitivity. So the ability to decode data with a bit error rate of less than 0.1% at a given signal strength is called the receiver sensitivity. Forward error correction, which is some maths, improves receiver sensitivity and lets devices be further away from each other. So it kind of looks like this. So without FEC, we're going to hit our black line, which is our bit error rate at some distance from the transmitter. These numbers mean nothing, by the way, it's nothing to scale here, but you can see the principle. But if I use the LE coded physical layer variant with forward error correction, I can get much further away because I can still decode my data correctly at a much lower signal to noise ratio. And in fact, the range of Bluetooth Low Energy today using FEC is over 1 kilometre. I actually saw a company who are a household name consumer electronics manufacturer present on this subject a couple of years ago, and they were getting 3 kilometres in their testing, which is pretty astonishing. So there you go. Right, mesh networking. So I want to quickly, because I'm running short of time now actually, introduce you to mesh networking and give you some insight into a bit of an edge case, something slightly more unusual. If you're not familiar with mesh networking at all, there are a number of low power wireless communication systems that let you form mesh networks. Mesh networks don't have a central point to them like a router or an access point or a hub or anything like this. The principle is like they're like a cobweb. The topology allows many-to-many direct communication between devices. Bluetooth Mesh has been around for about 3 years now and was designed in the beginning with smart buildings and smart industrial applications in mind. And a mesh network can have 32,767 devices in it, so that's quite large. It's for monitoring, controlling, and automating things in places like smart buildings, and it's message oriented, so devices send messages that are received and acted upon by other devices. Uses a publish and subscribe approach, so a device is said to publish a message to a given address, and these are normally group addresses. Other devices will subscribe to group addresses that they're interested in. The reason for mentioning this is it means that there is no central kind of brain in the system that knows all the configuration information, because that would be a central point of failure. It would be a problem to replicate around the network or something like this. It's very loosely coupled. You can make changes to your network with great ease without needing to do all sorts of overnight reconfiguration things which other mesh systems need. Yeah, I'll stop that. Just get moving on this, I think. So stack, that's the one we talked about already. That's connectable Bluetooth Low Energy devices, things like smartphones. Bluetooth Mesh sits on top of the Bluetooth Low Energy controller. So much of what I've already said actually applies. It has its own set of layers that occupy the host part though, and these are concerned with mesh networking, not just radio communications. Use cases in a Bluetooth mesh network are largely kind of machine-to-machine communication use cases, switches and sensors, dynamically controlling lighting systems and stuff like this. There are occasions, though, where human beings need a graphical user interface to control, monitor, configure the state of the network in a building, though. And that's okay because we can do that. Any mesh device in a network is called a node, and there are a number of features or network capabilities a node can be given through a configuration flag being set. It's just software. There are no special networking devices in a mesh network. One of those capabilities is called the proxy node. Oh, by the way, I forgot to tell you something really important. With a mesh network, you're not constrained by direct communication range. Messages hop across the network from device to device. So a mesh network can span a massive area, and messages effectively travel at the speed of sound across the network. So entire buildings, business campuses, they can all have a whole mesh network in them. And I mentioned that because relaying is one of these special roles. The role that lets you take a smartphone application which does not have Bluetooth Mesh APIs, write an app that can inject and receive mesh messages securely into a mesh network is through a feature called the proxy. So nodes can provide this proxy service, and they essentially have both variants of the Bluetooth stack on them, the GAP, GAT, and attribute protocol stuff we talked about earlier, and the mesh stack, and they kind of do some translation. When you're writing applications of this sort, your application will have to scan and connect to a proxy node. It has a GAT service called the Mesh Proxy Service, which has two characteristics, one for sending data into the network by writing to a characteristic, one for receiving messages out of the network in the form of Bluetooth notifications. There you go, just said all that. Quick demo of what this looks like, so you get an idea of this kind of thing in action. So I actually wrote this application. It's a Swift application running on iOS. I'm going to fire up a video now, actually, which is already running. Check this out. I'll talk you through it quickly. So what I'm doing here is mounting on a board 16 devices called Nordic Thingies. These are developer boards. They contain a Bluetooth module, which has an ARM processor. I've programmed them all using a real-time operating system and kind of runtime framework called Zephyr. It's open source, runs on lots of things, has a mesh stack. I've implemented what we call models. These are kind of application layer standard component types that allow me to switch on or off the LEDs which these devices have and change their color. So there's two separate models, the generic on-off server model and the light HSL model. HSL is hue, saturation, and lightness. Each device has then been configured using a smartphone application, that's how it's done, to subscribe each device to 3 different addresses. I've got one address which means membership of the entire grid, and then each device subscribes to an address which means membership of the column that it's in, and another address for the row that it's in. So here they go now being switched on and attached to a piece of cardboard because I'm such a proper engineer, me, bit of Velcro there as well, high-tech stuff. And here comes my app. So this is, again, an iOS application. It scans, it finds a proxy, it connects. Actually, the device at the bottom of the screen there is acting as a proxy. I'm connecting to the proxy. And now what I can do through my UI is I can select different destination addresses, which you'll see at the top of the screen there. DST is one of the field names, and transmit one of two message types. I'm going to send generic on-off set messages with a value of 1 or 0 for switch on or switch off, and light HSL set messages, which mean please change the color to this value. And if we watch what happens here, you'll get the gist of this. So there you go. I've just sent a message to the all nodes address to switch on and then switch off. I'm now going to select a different address. This is a column clearly, and sent an on message there. Only those devices that have subscribed to that address have responded. So this is the publish and subscribe mechanism working here. I'm now going to switch them all off, I think. There we go. Then I'm going to switch them all back on, and then I'm going to start playing with colors, and then I'm going to get back to my slides because time is short. So there you go. I've sent a different message type and changed the color. Now I'm hesitating, wondering what to do next. Ooh, it's a bit of a difficult decision here. Chosen a row address, changed that row only to red. So there you go. So that's the kind of thing that I'm exercising control over subsets of the network by using different addresses. What else might you see in the future? Another check of time again, we're okay. So, few things that have been going on in the world of Bluetooth just to be aware of. When new specifications get published, there's then always a delay between publication and manufacturers adopting a feature and you seeing it in products in the marketplace. It could take a couple of years or more sometimes. It all depends on complexity and product roadmaps and stuff like this. But things to know about. Bluetooth 5.1 introduced a high accuracy direction and location finding capability. It takes two forms, two architectures called angle of arrival and angle of departure. You can use this to determine the location of objects inside buildings, away from GPS line of sight and stuff like this, to within 10 centimeters. If I had more time, I'd show you this. It's really amazing. The AOA, AOD architectures concern which of the two devices, receiver or transmitter, contains an antenna array, and it uses radio phase differences to figure out angles. It's very clever, really cool. Audio. This is going to be enormous. So, audio has been the bedrock of Bluetooth forever, and I said right at the start here that the old Bluetooth BR-EDR is still used for audio. That's what I'm using today, so I really hope you can hear me. That would be ironic, but we're replacing it. So a new audio technology based on Bluetooth Low Energy is coming. It's called Bluetooth LE Audio. Some of the specifications for this have already been released. There's still some to come. It includes a new codec. That's my next slide, actually. Yeah, so it includes a new codec called LC3, higher quality, so that's nice. More interesting, though, are the fact that it supports new use cases, some connection-oriented, some involving broadcasting. One of the cool use cases is audio sharing. So rather than just one-to-one communication, say from your smartphone to your headset, like I'm doing now, actually from my computer to my headset, I could transmit my audio to multiple headsets, say to share audio with my friends. I could do that on a broadcast basis. I could broadcast the audio in a cinema to everyone's Bluetooth LE Audio headset. Better still, I can concurrently transmit multiple content streams concurrently. So maybe on an aircraft, I'm doing the safety briefing in different languages all at the same time, all conveyed by the same underlying mechanisms, and you choose the language, the stream you want to tune into. It's really cool. And last but not least, hearing aids, wireless hearing aids. Not really my field, but my understanding is that there is no standard for wireless technologies in hearing aids. Well, now there is. So this is going to have a massive impact. Not there in products yet, but that's coming. Under the hood, just so you know what makes this possible, key building block in the core Bluetooth stack is something called isochronous channels. Isochronous channels are communication channels which handle time-bound data. So in the case of audio, one of the primary use cases here, I could be transmitting data to multiple devices, but because of connection sharing, that data is going to arrive at different times at those different destination devices. But isochronous channels allow me to ensure that the rendering or processing of that data happens simultaneously. And of course, you'd want left and right stereo in your earbuds and your friend's earbuds and your friend's earbuds to render that audio at exactly the same time. And that's what isochronous channels lets you do. So if this has been at all interesting, if I've whetted your appetite, where else is there information? Well, we have a ton of it, actually. If you go to Bluetooth.com, highly recommended for developers, of which I am one, by the way, been coding since the 1980s. My first computer's on the wall behind you. You can maybe see that. Don't know if I duck down. Sinclair ZX81. Anyway, we have things called study guides. These are self-paced, kind of self-study educational resources. They all include hands-on project work. So if you're like me, and you can't just sit there and read and read and read, you like to do stuff, you learn best by doing, that's what they're for. So every topic pretty much that you can imagine is covered. One I definitely recommend, by the way, is the security study guide. Lots of myth, legend, disinformation about Bluetooth security. Even if you know nothing about security, the first module of that will teach you all the fundamentals and then take you through all the ways in which Bluetooth uses or makes available security features. So those are study guides. Sitting underneath on the slide here, we have papers. You all know what papers are. We have all sorts of them, including highlighted there, my paper on the subject of reliability. Faster way to learn. They're not a substitute for the formal specifications, but some of those are challenging and large. The Bluetooth core spec is 3,500 pages. My recommendation is find a paper, start there, read about the stuff you're interested in, get a solid understanding, and then when you're getting serious, reach for the spec. So, my friends, thank you so much for listening. Assuming anyone's still out there, I don't have you on screen, so I don't know, but I'm assuming some of you are still there. I'm going to switch over to Slack. So if anyone has any questions, I'm going to hang out on Slack for some time, an hour or so, let's say. And if you want to ask me any questions, fire away, and I shall do my utmost to give you rational and factual answers. Thank you again.